For most interstellar objects, the story is brief: a faint detection, a rapid flyby, a handful of observations before the object disappears forever into deep space. That was the case with Oumuamua. It was largely the case with Borisov. But 3I Atlas has refused to follow that script. New measurements, new analyses, new inconsistencies, so many, in fact, that the list of known anomalies has had to be updated yet again. According to the latest assessment, the number now stands at 18. 18 separate behaviors, properties, or coincidences that do not comfortably fit within standard cometary physics. This is no longer a case of a single odd feature that might be smoothed over with better modeling, nor is it a matter of one controversial interpretation driving the conversation. Many of these findings come from independent teams, published in mainstream scientific literature, and framed cautiously, often without any reference to exotic explanations. They simply report the same unsettling conclusion. 3I Atlas is doing things it should not be doing if it were a typical comet. That growing discomfort is precisely why the anomaly list has expanded again. As new data arrived, earlier observations had to be refined, subdivided, or reclassified. Some anomalies became more severe, others became harder to dismiss, and taken together, they form a pattern that resists simplification. A pattern that suggests not randomness, but structure. Not chaos, but repeated, low-probability alignments. This is why the object remains in the spotlight, not because of speculation about alien technology, but because the mundane explanation has to work increasingly hard to keep up. Every time the community tries to settle the matter, every time the phrase, "just a comet," is repeated, another measurement forces the conversation open again. Another paper lands. What first drew attention was not its brightness or its size, but its trajectory. Interstellar objects are expected to arrive from random directions, statistically aligned with the disk of the Milky Way, rather than the flat plane in which the planets orbit the Sun. 3I Atlas did not do that. Instead, it arrived on a retrograde path, aligned within a few degrees of the planetary orbital plane itself. The odds of that alignment occurring by chance are small, but not impossible. On its own, it might have been written off as an unlucky coincidence, but trajectory turned out to be only the beginning. As its path through the solar system was reconstructed in greater detail, a striking picture began to emerge. The timing of its arrival placed it near Mars and Jupiter at distances that were close in astronomical terms, while also ensuring that at perihelion, the point of closest approach to the Sun, it would be poorly positioned for direct observation from Earth. It passed Venus at less than 1 astronomical unit. It skimmed regions of the inner solar system that are disproportionately rich in scientific interest, including the Jovian system, whose icy moons are among the most promising locations for subsurface oceans and potential life. None of this proves intent, but the geometry is undeniably neat. One particularly eyebrow-raising coincidence involves Jupiter's Hill radius, the boundary at which the planet's gravity balances that of the Sun. The predicted close approach of 3I Atlas in March 2026 places it almost exactly at this gravitational threshold. These regions are not arbitrary. Human space agencies deliberately position spacecraft at similar balance points because they are ideal locations for long-term observation and minimal fuel expenditure. That an interstellar object would naturally pass so close to such a dynamically useful region is, again, not impossible, but it adds to a growing sense that chance is being asked to do an increasing amount of explanatory work. Then there is the anti-tail. Comets, when heated by the Sun, typically produce tails that stream away from it, shaped by solar radiation pressure and the solar wind. Anti-tails, features that appear to point toward the Sun, are usually optical illusions caused by viewing geometry. They are not physical structures extending sunward. Hubble Space Telescope images of 3I Atlas challenged that understanding. Before perihelion, it displayed what appears to be a tightly collimated sunward-pointing structure that was 10 times longer than it was wide. Post-perihelion images showed similarly structured features extending for hundreds of thousands of kilometers. No known comet has been observed producing a physical jet like this without projection effects being responsible. The geometry of this jet raised further questions. As the object rotated, the jet appeared to wobble, implying a very specific alignment between the jet's base and the object's rotational axis. The probability that the jet's source would lie within a narrow angular range of the sun-facing pole is extremely low. Yet the same configuration appeared again after perihelion, now seemingly originating from the opposite pole, as though the system had flipped while preserving its overall symmetry. For that to happen, the rotation axis would need to shift by a very precise amount during the closest approach to the sun. According to the data, that is exactly what occurred. Symmetry continues to appear where randomness would normally dominate. Image processing techniques applied to Hubble data revealed 3 smaller jets emerging from the nucleus, evenly spaced at 120-degree intervals. Such geometric regularity is uncommon in natural cometary activity, which is typically chaotic and irregular, driven by patchy outgassing and heterogeneous material. The launch points of these jets also present a thermal puzzle. They appear to remain active only when facing the sun, despite spending long periods on the night side of the object. Maintaining such behavior would require an insulation efficiency that natural cometary material is not known to possess, as heat readily conducts through porous ice and rock over timescales of months. Even gravitational effects seem to align too neatly. The amount by which the object's trajectory was deflected at perihelion matches, almost exactly, twice the opening angle of the observed jet. This relationship allows the same jet geometry to be maintained before and after perihelion, despite the object's orientation changing relative to the sun. It is a mathematically elegant coincidence, but elegance is not a typical hallmark of natural, uncontrolled processes. As January 22, 2026 approaches, yet another alignment adds itself to the list. On that date, Earth, the Sun, and 3I Atlas will line up to within less than a degree. At precisely that time, the antitail will be oriented directly toward Earth, making it exceptionally difficult to observe. Once again, a key moment coincides with reduced visibility, echoing the object's unobservable perihelion passage months earlier. Some coincidences verge into cultural territory. The incoming direction of 3I Atlas aligns within several degrees of the location associated with the famous 1977 WOW signal, a narrowband radio burst that remains unexplained decades later. Few scientists would argue that this alignment has any physical significance, but its presence in the overall pattern contributes to the uncanny narrative surrounding the object. Trajectory and geometry alone would already place 3I Atlas among the most unusual interstellar visitors ever observed. But composition complicates the story further. Spectroscopic analysis of the gas surrounding the object revealed an unexpectedly high abundance of nickel relative to iron. This ratio is not only unusual among comets, it more closely resembles industrially produced alloys than known cosmic material. The nickel-to-cyanide ratio exceeds that of thousands of catalogued comets, including the previously observed interstellar comet Borisov. The antitail itself presents a mass problem. To push through the solar wind and radiation pressure over such vast distances, the particles composing it would need to be significantly larger than the sub-micron dust grains typical of cometary tails. But if the particles are that large, the total mass required to account for the observed brightness becomes implausibly high. In simple terms, either the particles are too small to survive, or there are too many of them to be physically reasonable. Observations from the Sphere-X Space Observatory added yet another layer. Before perihelion, icy fragments were detected in the vicinity of the nucleus. After perihelion, those ice signatures vanished, replaced by complex organic molecules and a dramatic 20-fold increase in water production. For such organics to survive an interstellar journey lasting potentially billions of years, they would need to be shielded beneath a substantial layer of material, far deeper than the surface layers typically exposed on cometary nuclei. The physical properties of the object as a whole also defy easy categorization. The nucleus of 3I Atlas appears to be more massive than those of both Oumuamua and Borisov, yet it is traveling faster than either. Given how rarely interstellar objects are detected at all, this combination raises the possibility that it was not randomly drawn from a generic population of interstellar debris. Its polarization signature strengthens that suspicion. It exhibits extreme negative polarization, a behavior not observed in any known comet, including other interstellar ones. Near perihelion, it brightened faster than any comet on record and displayed a blue coloration indicating temperatures hotter than the Sun's corona. If the anomalies stopped there, the debate would already be intense. But recent observations have added a new and deeply puzzling dimension: rotation and pulsing. Brightness variations in comets are normally easy to explain. As the nucleus rotates, active regions rotate into and out of view, producing periodic changes in luminosity. In 3I Atlas, brightness does vary periodically, but not in sync with its rotation. Two independent methods have been used to measure its rotational period. One tracks the changing orientation of the jets as the object spins. The other analyzes the periodic rise and fall in overall brightness, including the coma and jets. After perihelion, both methods converged on a rotation period of about 7.1 hours. That alone is notable because it represents a speed-up relative to the object's pre-perihelion rotation. But before perihelion, the two methods did not agree at all. Jet motion suggested a period of roughly 7.7 hours, while brightness variations implied a period of 16 to 17 hours. This discrepancy was reported in independent scientific papers, not associated with any single researcher or hypothesis. If brightness variations reflect rotation, then 3I Atlas would have had to more than double its rotational speed over a short period of time. Such a change should subject the nucleus to stresses capable of tearing it apart, yet no such disruption has been observed. The alternative is even stranger. The pulsing brightness is not caused by rotation at all. That raises a simple but unsettling question. If rotation is not driving the pulsing, then what is? The recent convergence of the two measured periods after perihelion suggests that whatever mechanism is responsible for the pulsing has changed its behavior. The system appears to have corrected itself, bringing brightness variability back into alignment with rotation. No known cometary process predicts such behavior. Throughout this unfolding story, one constant remains. Despite the growing body of data, the prevailing narrative from mainstream institutions continues to describe 3I Atlas as a normal comet with a few unusual features. That description becomes increasingly difficult to sustain as the list of anomalies grows longer and more interconnected. 18 distinct deviations from expected behavior do not describe a minor outlier. They describe something fundamentally unfamiliar. None of this constitutes proof of an artificial origin. Extraordinary claims still require extraordinary evidence. But the scientific discomfort surrounding 3I Atlas does not arise from speculation. It arises from observation, from published data, from measurements taken by some of the most advanced instruments ever built. As researchers like Avi Loeb and others continue to analyze the data, more papers will follow, each attempting to reconcile these findings with known physics. Whether the final explanation involves exotic natural processes, a previously unknown class of interstellar object, or something even more surprising, one conclusion is already unavoidable. We have never observed anything quite like 3I Atlas passing through our solar system. That alone makes it worthy of sustained attention. This is not a story that will resolve quickly. The dataset is vast, the questions are fundamental, and the implications extend beyond any single object. For now, 3I Atlas continues on its path, pulsing, rotating, and defying simple explanations, leaving astronomers with an uncomfortable reminder that the universe is under no obligation to conform to our expectations.